Okay, we know how to find limit values using a graph, but it's kind of tedious if we have to draw a graph every single time, especially sometimes some graphs are harder to draw and we can't draw the exact graph. So instead, there turns out to be a set of limit properties that help us solve the limits algebraically without graphing, which is super helpful. So let's pretend for a second that the limit as x approaches a of f at x and the limit as x approaches a of g of x both exist. Okay, so these limit exist. Then these are the limit properties or limit rules that we have. First, we have a constant multiple rule. It says that if I want to find the limit of a constant times a function, I can actually pull that constant out to the front and just find the limit of my function and then multiply them together. I also have limit sum and difference rule. This one's intuitive as well. If you want to find the limit of f at x plus g of x or f at x minus g of x, you can actually find the limit of f at x, find the limit of g of x, these are both just numbers, and then either add or subtract them. We have limit product rule. So if I have the product of two functions, meaning two functions being multiplied together, and I want to find the limit, I can actually find the limit of each function first, which will give me numbers, and then I'm multiplying these two numbers at the end. Limit quotient rule, meaning I want to divide limits. So I'm dividing two functions. I can find the limit of each function, which are two numbers, and divide those two numbers. There is one note that we have to make for limit quotient rule, and that is that the limit as x approaches a of g of x, whatever this finite number is not 0. Because, of course, we can't divide by 0, right? So if we have a limit where this equals 0, this does not work. And finally, we have the limit power rule. So I could find the function raised to some power and then find the limit, or I can find the limit of the function first, get that number, and then take the number and raise it to a power. Okay, with all the limit properties that we learned on the last page, we're going to put this all together using something called direct substitution. This is super, super, super important. Whenever we have a limit question, that is always the first thing I want you to try, direct substitution. Okay, so how does it actually work? Well, if I'm looking for the limit as x approaches a of a constant, that's just going to be the constant itself. And if I'm looking at the limit as x approaches a of x, that's going to be a itself. Meaning that whenever I'm giving a limit, I always want to just substitute the value of x directly into the expression. So just take whatever x is and sub it into the expression if you can. If you get a number, that's it, that's your limit. If you get something weird, then we have to do a little bit more work. Okay, that's called direct substitution. And there are two notes I want to make about this. Number one, if you ever end up with the square root of 0, be very, very careful. I know that the square root of 0 is 0, right? But because we're looking at limits here, we're not looking at exactly the value 0, we're looking at something really close to 0. So guess what happens when we're looking at the limit from the left as x approaches 0 from the left? I end up with the square root of a negative number, which is not defined. So whenever you end up with the square root of 0, I want you to check the left and right hand limits separately to make sure the limit exists. Another note I want to make is for this weird looking 0 over 0 thing. If you do your direct substitution and you end up with something that is 0 over 0, this is called an indeterminate form. Then what we have to do is we have to manipulate the expression, simplify it, and then evaluate the limit again, do a direct substitution again. So you might be thinking, what is the 0 over 0 thing, Jess? Like, I thought you can't divide by 0. You're right, we can't divide by 0. If I actually have a number divided by the number 0, that is undefined. But we're talking about limits here. So I'm not saying the number 0 divided by the number 0. I'm saying something really, really, really small divided by something really, 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 really small. In that case, we don't know what happens. We have to do some work to evaluate the limit. There are other weird forms like this as well. There's the 0 over 0, 0 times infinity, infinity minus infinity, and these exponent ones. Some of these we will cover in later chapters. Some of them we won't cover in this grade 12 course at all. You'll see it in first year university.